Yeah, you can use the flat variable instead, or you can use 0 or 1, or you use true or false, whatever. Yeah, it's free, right? It just remark that okay, okay, this is already visited. Okay. So yeah, so to check the visited, one easy way you create array of the length of the vertices, and if they are visited, the index will be corresponding to the, for example, number here, or the label here. For example, the first one is corresponding to the first node. Yeah. When you visit, you make it 1. If not, you make it 0, or you make it true or false or whatever. Yeah. You can also put the flag inside the struct. Also, you can put the flag inside the struct also. Yeah. But because when you want to check it, every time you need to check it visit or not, right? If you put in the struct, you need to traverse the struct, traverse the node. Yeah, it may take time, or you can just make the independent array. Then you can access it instantly, right? The size of the tree, yes. Oh, you know, right? Because when you create a tree, we have the number of the node in the tree. You remember? If you look at when you do the lab, you remember in the tree we have the number of the vertices, right? So we have we have the number of the vertices in the tree. Yeah. What is the graph hay the loop? How we go back? That's why I mentioned, right? That's why you look at you have the visiting array. Even though the loop, right? For example, 11, then the next is 1 and 2, right? And you visit 1 and you visit 2. Then after that, you visit the neighbor 1, right? But the neighbor 1, you have the loop, right? 1 connect to 2 again. But you already know that 2 already visited. So you don't put 2 into the queue because 2 already visited. Okay. So we only put into the queue if the node has not been visited before. Okay. We better it up to you. I mean the array should be better. Okay. Array should be better. We just store one array, and then you can access it instantly also. Okay. Marking is just, the marking is just a way we mark, right? You can use array. You can create one element inside the struct node also. Whatever. Marking here is just array. We put okay, have some way we know that it is already visited for the node. Okay. So what the real implementation is up to you. You can use array like I mentioned. You can create one instance inside the struct of the node. Okay. So which one more convenient? But to me, like array, you create an individual array should be more convenient. Array means that, whenever you visit, right? For example, you have the trail node here, right? Then you create the array, initialize the array with the trail node, okay? Then the index will be the node label. For example, the first one will be corresponding to first node, right? And the size will be trail here, right? Okay. So whenever you visit for example, you start with the 11, then you put the 11. At first it's on 0, for example. It means that have a visit. Then you start with 11, you mark it a visit, right? So you change the array, the value of the array at 1. Okay. The marking or the array, it on about it depends on your implementation. If you put one marking inside the struct node, then maybe you need to get the struct node depend on the way of the graph representation. Okay. Then if you put like array like this, right? If you visit the node 1, so you just mark, you change the value of the array of the first node A1. Okay. Normally, right? Normally we assume that all the node label are different. Okay. So it means that they should not have the same label. Okay, and because in this course we make it easier, right? So for example, if we have the trail node, then the label should be from 1 to trail, just for easy convenience. Okay, and the label should be different. Okay, because we're more interested on the algorithm, right? So we just make convention naming. So for example, if the graph have the trail node, then the label should be from 1 to trail. Okay. Okay, so that's it for the breakfast search. Then we continue with the depth first search. Okay, the depth first search it works similar to the pre-order traversal of the tree. So for the depth first search, right? Okay, I make a simple illustration here. For example, you have the graph, but because for the illustration, right, we just consider like it like a tree. But I mean the way simple. But I put like a tree, right? For the breakfast search, you will start with this one. For example, your starting point. So the next one you will traverse the neighbor, right? And the next one we will traverse this one on the neighbor. So that was the breakfast search. You search in depth. Okay. You search on the in depth first before you go deeper. Okay. But for the deep first search, it's a bit different. Okay. For the deep first search, it search in depth rather than in wide. Okay. Breadth first search, they search in wide rather than in depth. But depth first search, you go in depth first. Okay. For example, you have, for example, the graph, something like this, right? Okay. Then how you search in this graph? So if you start from this node, right? So you go this one. For example, this one and this one are neighbor. So you choose one. Okay, the order is not important. Okay. For example, you go this one. You traverse this one first. Then for the breakfast search, you will traverse this one next, right? But for the depth first search, you go depth. Go deep until they cannot go further. Then you go back. Okay. So this one, you will traverse this one first. And for example, you will traverse the neighbor. Then instead of the next one traverse a neighbor here, it go deeper. Okay. So for example, it will go to here, traverse this next. And then now it cannot go further, right? It backtrack to the not to and go to the other way 4. Okay. And for example, if 4 can have the diff, they just go further and further until they cannot go deeper anymore. They go back. Yeah. For example, 6 cannot go back anymore. Cannot go deeper anymore. So they go back to 5. 5 cannot go anymore because you already traversed the 1, 2, 3, 4, 5, 6, right? You go back 4, go back 2, go back 1, and now we go to other branch. It traverse 7 here. Then 7, it will traverse the 8 here. Okay. Then 8 cannot go deeper. Then it go back to 7. It go to the other branch 9. So that's a way for the default search. It means that for the default search, right? If you have a way to go deep, then you just go that path, go deeper until you cannot go furthermore. Then you go back one more step. Then you go to the other way. Okay. So that is the default search. So understand. So you can consider this like the you are solving the a maze, right? Or you are going in a maze, right? For example, you go in a maze, then you have 2 ways to go, right? How to draw? Okay, you have 2 ways to go. Okay, and every time you have 2 ways to go, right? Yeah. So if you go here, right? So you just choose one step to go, right? So you go this one. For example, you go on the left hand side. Okay, go here. Then you have 2 ways, right? Left hand side or go straight here. But for example, you follow this one. Then again, you have 2 ways, right? Then you just choose one to go. For example, go. And if here you stuck here, then you just go back, right? You just go back. then you go to the other way. Yeah, just like explore, right? So you go deeper, deeper until you stuck, then you go back. Okay? Back one step, then you go the other way. So that's it, the depth first search. Okay. So you go as deep as possible. Okay. Before you until you cannot go anymore, then you go back. You go try the other path. Okay. So for example, for the 11, for example, this one I mentioned, right? 11. You start with 11 first. Then the next one, because 11 have the two neighbor, right? 1 and 2. So you choose one, either 1 or 2, also no matter. Okay. For example, you choose 1 to go. Then the next one, because you go to 1, right? Then you have 3 neighbor, right? 2, 3, 4. Then it's up to you to choose. Okay. But you can choose any. For example, you choose 4. Okay. Then you go choose 4, right? Now you cannot go further anymore. Right? Then you go back to 1. Okay. Go to 4. Cannot go anymore. Back to 1. 1. Then you go to the next one. Next one you can choose. Next one up. 1 will be 2 and 3, right? For example, you choose a 3 to go. Okay. Then 3 can go further. Then you can go 5, 7 and 8, right? For example, you choose a 7. Then 7 you stuck. You cannot go furthermore. Then you go back to 3. Then you go the order not of 3 is 8, right? Okay, go 8. 8 can go furthermore. Go to 12. Then 12 stuck. Okay. Then you go back to 8. 8 also stuck, right? Because you already traversed on the path. You go back to 3. 3 also stuck, right? Because you already traversed the 7, 8, right, and 1. So we go to the 1. Okay. 3 stuck. Then go to 1. Now 1, you already traversed the 4, 3, and 11, right? Then the only way you go is 2. Yeah. Similarly, 2, you have 2 ways to go, 5 and 6. You can choose one. Any, for example, 5. 5 stucking. 5 you are stuck. You back to 2. 2, now you only have one more way to go, 6. Now you have the 9 and 10, right? Then for example, you choose 9, stuck. You back to 6. You go to 10. Yeah. And that's it, the way. Understand? So the first one, if you have a few neighbors, you just choose one neighbor and then go on the way to this neighbor. If you start on the way, you backtrack, you find another path. Okay, it's just like you're exploring a maze. Okay, then just choose one way to go. Stucking, go back a little bit, go try another way. Okay, so it's clear, right, for the depth search. So how to implement the depth search? So you remember for the breadth search, you keep a queue. For the depth search, you keep a stack. Okay. A stack is used to monitor which vertex you visit next. For example, you start with A. For example, this route, you start with A. So you just create a stack. Okay. So you put A here. Okay. Then you see all the neighbor of A. Neighbor of A will be B, C, and F, right? Next, B, C, and F. Then you choose one to go. The order is not important, but for example, you choose B. Okay, so you put B on the stack. Okay, then now you mark B already visit, A and B already visit. Okay, so visit one is the purple one. Okay, then purple or pink, whatever. Okay, anyway, purple or pink color. Okay, then next you see all the neighbor of B. For example, C and D, right? Neighbor of B is C and D. So you choose one. For example, we choose B. Then we C and D, so we choose C, for example. Then you put C on the stack. Okay. Now you stop at C. C can go anywhere else? No, right? Because from C you cannot go anywhere else. It means that you start from C. So when you start from C, right, you take away C from the stack. take away. Then you go back, take away from the stack, and then you pick the head of the stack. Now B. This means that you go back to B. Okay. Now it's B. Then you check what is the neighbor of B that haven't visited yet. So now we only have D, right? Okay. Remember the stack is B and A. Okay. Now we choose another way. This is equal to B, D. So we highlight. Okay. I just redraw a stack. Currently we have the A and B. Okay. Now, because the neighbor of B is D, so we put D into, we choose to go to D, okay? Then next, D can go anywhere, haven't visited, because D can go to A and C, but A and C we already mark it a visited, right? So it means that we start at D. When we start, we take away it from the stack. Now the current head of the stack is B. Okay. Then we check from B. B whether we can go anywhere that haven't visited. No, right? Right. B start at B. Now B cannot go anywhere else. Then it means that we also start at B. Okay. Start at B, it means that we need to erase B from the stack. Now with the head of the stack is A. Then we see any other neighbor of A that we haven't visited yet. That's F, right? Only F. So we put F into. Okay. Then we go to F. Then F can go anywhere that haven't visited yet. F can only go to C and A, but C and A we already marked it a visited, right? Then it means we are stucking at F, right? F have no way to go. If no way, then we remove it from the stack. Okay. Now the head of the stack is A. Okay. Then we see at A. Can we go anywhere from A right now? No, right? Because A we already traversed the B, C, D, B, C, F, right? A can only go to B, C, F, but we already traversed the B, C, F. So it means that we are stucking at A. Stucking at A, then we erase A from our stack. Okay, so we create A. Now the stack. Now our stack is empty. This means that no more vertex to traverse. Then we stop. So it means that from A you can traverse what? B, C, D, F. And remember, you cannot go to H and E, right? Because you have no way from A to go to H and E. Okay. So you can only traverse the B, C, D, F. Okay. B, C, D, F, yes. You cannot traverse the E and H. Okay. That's the way that the DFS search go. Okay. And remember, yeah, because the H and E cannot reach from the A, so it means that this directed graph is not strongly connected, right? Because strongly connected means that from any node you can traverse to other nodes, but from A you cannot traverse to E, so that's why it's not strongly connected one. Okay. This means that you can also use a DFS search to check whether the graph is strongly connected or not, right? Okay. So now you clear about the DFS search, right? Yeah, this is the post order. They're very similar to the post order reorder. I think they are like similar to the pre-order, not the post order traversal. Yeah, pre-order traversal. Yeah, similar to the pre-order traversal. Okay. Yeah, the same methods. Yeah, of course, the same methods can also work for the undirected graph. You just check the neighbor, right? the result is not unique, you mean that I mean for the depth first search, it's more about the traversal. It means that at the end, how many nodes you can traverse from the original node, right? But the order of the visiting, it depends to you, right? Because I mentioned, right, the ordering is not important because we haven't considered the ordering. So if A have two nodes, B and C, you can choose any order to go, B or C. Okay. So if we're pushing all the neighbor to the stack, right? It's more. I mean, it's not about the depth anymore. Okay. You can. I mean, this is the illustration, right? You can see if you put on the neighbor, if go to the stack, it's not the depth anymore. Okay. You can try out later at the end of the lecture. You can see. You can try. It's not the depth anymore because depth means that you need to go all the way on the way deeper, the much deep I mean the deeper as possible, the more deeper as possible. If you put on the neighbor go to the stack, it's not the difference anymore. Okay, so the ordering here, yeah, I mean I have for the difference because the purpose for the breakfast or difference is just whether you can traverse the graph or not. So the path may be not unique if you choose a different order of the neighbor, right? Because A can be connected to B and C. So you want to go B and C, you are free to go. Yeah, I mean. So if you go to the B, then the order different, right? If you go to B, then C maybe go. Yeah, of course, I will release the code for the breakfast. So no worry about that. I will release the template like for the hash and representation. I also release the template for the breakfast search and depth search. Okay, but the idea is like that. For the depth search, you keep the stack. For the breakfast search, you keep a queue. Okay, and how it goes, I also explained to you, right? How to pick up from the stack or from or the queue or whatever. Okay. But I mean the code I will release in the assignment 5, okay, the template for you. So you just fill in some function. Yeah. Okay. So that's the general, the pseudocode for the depth search. I just mentioned, right, you create a stack, and every time you you pick the stack, haven't take out yet, you just pick it because we need to backtrack later, right? You just pick one node, and then you see the neighbor, and you choose one neighbor to go. Okay, you choose one neighbor to go, and if you choose this neighbor to go, then you put this neighbor into the stack, and you just go. And if you go one way and you stop at one node, right? Then you cannot go anymore. You are stucking. You stop, right? You have no way to go more. Then you take away this node from a stack, throw away. Okay. Then you pick the top node in the stack to go. It means that we go further stack, we take away it from the stack, and then we backtrack to the previous one and choose the other path to go. Yeah, just I mean the idea. Yeah. Like I just illustrate for you, right? Okay. If we are stucking, cannot go further, then we take away this node from the stack, and then we do the picking to choose the current top of the stack to go. Okay, so clear, right? Yeah, also the final lab with the test, whatever, I will revise the template. Yeah. And the question in the assignment or question of the final test will be also follow the question from the lab. Okay, so no worry. Okay, so usually I just ask you to implement some additional function. Okay, It's just like the assignment 5, right? Just add use additional function. But the format or the template I wrote by. Okay, good. So we yeah, just some notice, right? Like I mentioned, if the vertex has several neighbors, so it's okay. The order doesn't matter. You can travel in any order. Okay. And if the graph is strongly connected, right? Like if the graph, for example, this one, you can check, yeah, strongly connected, because any pair you can have a way to go. Okay. For example, from D to F, you can have one way to go, right? For example, if you want to traverse from F to D, so you can go this way, and then this way, and then this way. Yeah, any pair of the node, we have the path to go. So they are strongly connected graph. Okay, and if you apply, like I mentioned, like if that strongly connected graph, the depth search can use to detect this one. And after you apply the depth search, the way you go will be, they call it the depth search tree. The spanning tree you achieve is, they call it depth search tree. Okay, just I mean the calling the name. Okay, so if you apply the depth search in the strongly connected graph, the final spanning tree, you can call it a depth search tree. Okay. Remember, the breakfast sort also can be used to check whether the graph is strongly connected or not. Okay, and this one we call it the breakfast search tree. Here we call it a depth search tree. If you apply depth search, you call it a depth search tree. Apply the breakfast search, yeah, breakfast search tree. The searching is in ascending order, as I mentioned, right? If the question doesn't require, then it's okay. It's okay that you can go any order. You can go ascending order, you can go descending order, or you can go mixing order. You can go, for example, the neighbor is 5, 6, 7. You can go 5 first, 6, 7. Or you can go 6 first, 5, 7, whatever you like. Okay, it doesn't matter. Unless the question tell that you must go to the ascending order, then you go to ascending order. Otherwise, you can free to go any order. Okay. And the application for the depth search, we can have some application. For example, you can use it to find the topological sorting. Topological sorting means that you sort it in the array, and the previous elements will be the parents of the later. I mean, if 6 can be reached from 7, then 6 must be happen after the 7. For example, in this array, right? For example, 4, you can reach, 4 is after 7, right? From 7 can go to 4. So 4 must be after the 7 in the array. Okay, something like that. Okay, there is some, I mean, the application for this one. But anyway, they call it a topological sorting. Okay, then the depth search can use to create this kind of the topological sort. Okay. Topological sort is just like the ordering. Yeah. Okay. On the left hand side will be the higher order, and the right hand side. Okay. This means that if there's a path from, for example, from 7 and 2, then 7 must happen before 2 in the array. Okay. And it also can find the connected communion, like we just mentioned, right? If there's connected communion, we can find it. Or it can find the articulation point or cut vertex of the graph. Why the articulation point or the cut vertex? It means that there's some graph, right? They are connected, okay. But if you, for example, this graph is connected, right? But if you take away one node, for example, you take away this graph is connected, right? But if you take away this node, then the graph become unconnected, right? Because it becomes the two independent communion cannot connect it because you remove this one, did not. Okay. So this one used to find the cut, they call it a cut vertices. So this not equal a cut vertices. It means that if you remove this, the graph will be cut into the different component. Okay, it's not connected anymore. So this is some why the application for this one. It's not something like you have the electric graph, right? There is some electric graph, so they need to connect it, right? So you want to find some weak point. It means that some point that if there's some problem with the electric there, then the whole network will be disconnected, right? So we need to find some key point or key vertex like that. Okay. So in the electric graph, right? For example, the electric connection, right? We avoid some cut vertices like that, because if there's some problem with this node, right, the whole electric system will down because they're not connected anymore. Okay. And like I mentioned, we can also use to find a strongly connected component if they are directed graph. And yes, it can be used to solve the puzzle, right? Or the maze, like I just mentioned, right? When you go to the maze, you can use a depth search algorithm to solve the maze or the puzzle. This means that we try all the way. Okay, if cannot, then go back a little bit, try another way. Okay. Okay, so why the time complexity of the depth search? So the depth search, you see, right? We start with a node, then we visit the other node exactly one time, right? Right. And for the edge, we also for the edge, you remember, right? For the edge, we go and sometimes we need to go back, right? Right. One in the forward, right? And if it's stucking, then we go back, right? So it means that for every edge we traverse two times, right? One in the forward way and the one in the backward ways. Okay. Anyway, if you use the adjacency list, right, the time complexity will be OV plus E because you visit every node exactly one, right? So they are E. And for every edge, you visit two times, right? So they are OV. But if you use the adjacency matrix, time complexity OV squared, why? Because even though the depth search or the breadth search, you remember, right? When you go to one node, you need to see which node are the neighbors, right? Okay, but how to check the neighbor in the adjacency matrix? You remember adjacency matrix, for example, for this node one, right? How to know what is the neighbor? You have no way, right? Because you need to traverse on the array here, right? To pick up which one is the one is neighbor, zero is not neighbor, right? But you need to traverse on the array, right? For each, if you check the neighbor for one node, you need to traverse the array. And what the size of the array is V, right? To check for the neighbors in the adjacency matrix, you need to traverse the V array to check to pick up which one is one is neighbor, zero is not neighbor. Okay. So for every node, to check the neighbor, you need the V search, right? Search V time. Okay. V comparison, right? To check the neighbor. How many nodes we have V? So that's why to check the neighbor, you need the V square already. Okay. Plus the complexity of the of checking the edge, right? Every time you check the edge two times, right? So edge. And remember, right? The edge, the maximum number of the edge we mentioned, right? Is also the maximum number of the edge in the graph, right? Is what? Maximum number of the edge will be V times V. Actually, it should be because one edge can maximum connect to the order V minus one edge, right? So it should be the V times V minus one, right? divided by 2 if they're connected. Okay. If they are the undirected graph, so the number of edge will be times v minus 1 divided by 2, right? One edge connect to all the other v minus 1 edge. Okay. So the maximum number of edge also the v square, right? So it means that v square plus 2e also the ov square. Okay. Right. Anyway, it's a 2v square, something about 2v v square. So it also ov square. So if you use the adjacency list, time complexity is ov plus e. If you use the adjacency matrix, the time complexity is ov square. Okay. So that is the complexity for the depth first search. It's very similar to the complexity for breadth first search, right? So in summary, right, we have two ways to implement the graph traversal. First is a breadth first search. Second is the depth first search. Breadth first search means that you go wide. Depth first search, you go deep. Okay, one is go wide, one is go deep. Okay, to the breadth first search, you use the cube. For the depth first search, you use the stack. Okay. So for the breadth first search, you can find the sorted path. Yeah, and for the deep first search, you can use to solve some puzzle. Okay, and the complexity for both are the same. If you use the adjacency list, the complexity will be OV plus E. If you use the adjacency matrix, the complexity is V square. Okay. Yeah, I think that's the end of the lecture today. So we have some time. Yeah. So free to ask. Okay. Ask about the lecture, ask about the assignment or something. Okay. If you don't have any question, you can leave. No worry. So if you want to ask, you just stay here to ask me. Yeah, free to give any question. Okay, one by one first. Time complexity of the adjacency list, right? For the adjacency list, how you find the neighbor of the node? The neighbor of the node, you can find the neighbor very easy, right? You just go to the index, then you pick up on the node in the linked list, right? So yeah, instant time, right? So then for the adjacency list, because for the graph, we need to traverse on the node one time, right? So there, O V, right? And for the edge, you need to go forward, and then if stuck, you go back. So for every edge, you need to traverse 2 times. So the complexity will be V plus 2E. But because for the complexity, you can simply make like V plus E. Okay. So there for the adjacency list. Okay. So when the assignment 6 coming out, assignment 6 will be released next week, next Friday. Okay. And also the deadline will be also 2 weeks later also. So now the every assignment will be released on the Friday. Okay. So which is used for depth first search, list or matrix? You can use both. I just mentioned. But like for the complexity, normally we use the matrix better because of matrix. We use the list better because the list you have the less complexity, right? It's just a V plus E. For the if you use the matrix, you need complexity is V square. But you can use both. I mean, of course you can use both. But it suggests that you should use the list better because they have the lower complexity. But of course, no one force you to use list or matrix, right? Okay, so you can use both. No problem. The depth first is pre-order, right? Because you go deeper, right? Because every node you pick up one, right? And you go to this way to go deeper. So there should be the pre-order. The post-order is more about the breakfast search, right? The post-order means that you travel on the neighbors at the center. I mean on the neighbor before you go deeper. So if you go back to see the pre-order and post-order, you can see pre-order you can go deeper. You choose one path to go. Like the tree, right? You choose one path to go deeper and deeper. For the post-order, you choose the neighbor, okay, or on the children to go. Then after you traverse on the children, you go further. If you write down, you can see the order. So the default search is the pre-order, the breakfast search is the post-order. Right. Sorry, the breakfast search is the level order, yeah, level order, and the default search is post-order. And if you write down the formula, you can see, you can just do some symbol illustration, you can see. You just make like a few nodes, like the tree with a few nodes, then you can see the post order. Yes, correct. The time complexity for the default search, if you use the list, right, it's a V plus 2E. But because for the simplicity, right, complexity, you can remove the 2. So V plus E. Okay. But yeah, it's correct a V plus 2E. Because for each edge you traverse for work, and if you start, you go back, right? V plus 2E. On slide 15, let me see. Slide 15. The left hand side, yes, it is strongly connected graph. Because for any pair, you can find the path to go. Okay, it is strongly connected graph. You can see any pair of the vertices, you can have one path to go. C cannot go to all the vertices. Oh yeah. You are true. I think there's some typo here. The edge between A and C should be reversed. Sorry. Yeah, A and C, the path between A and C should be reversed. So C should move to A, not A go to C. Yeah. This is the typo. Yeah, I will correct it. Oh, sorry. Yeah, thanks for figuring out. Yeah. It should be the path from C to E, not C to A, not A to C. Okay. Then the graph is strongly connected. Okay. So there's a typo. Thanks for figuring out. So there the graph, there the path from C to A, not A to C. Okay. The time complexity for the breakfast search, the same, right? For the breakfast search, you also visit every not one time. So it's V, right? And for the edge, right, you visit one time. So it's V plus E also, right? Right? For the breakfast search, you traverse one time for every edge. Yeah. There's no backtracking, no going back. Okay. Yeah, similarly, yeah. For the depth first is V plus 2E. For the breakfast is V plus E. But because in the complexity, right, you can remove the number 2. So we just make it simply like V plus E. Okay. Okay, I think I can stop the recording now.